Welcome to Lecture 30. This is a lecture on Landau-Zener tunneling. This is a very famous problem that was solved originally in the early 1930s, and it's again one of the few time-dependent problems that has an exact solution. To give you a little bit about the history behind this, a very famous physicist named Landau approximately solved this problem, but he made some errors in his solution, and a German physicist named Zener re-examined the approach, recognized that the differential equation that one needs to solve for the time evolution is a differential equation that is one that was studied by mathematicians. It's not one that's very well known. It's called the Weber equation. And he found by looking at the solutions of that equation, which are called parabolic cylinder functions, he could determine the asymptotic behavior of the solutions at long times. Now, that is a rather technical and rather tortuous path to take to understand the solution of the problem. We're not going to go through that here. Instead, we're going to motivate how this works by the work that we did with cyclotron resonance, and then we're going to focus on how to understand the solution of this problem approximately. So let's start by looking at our cyclotron resonance problem. In the cyclotron resonance problem, when we went to the rotating frame, we found the Hamiltonian could be written as minus h bar big omega minus little omega times sz minus gamma b1 times sx. And in this case, b0 was equal to h bar big omega over gamma. That was the stationary field in the z direction. b1 was the rotating field that rotated at a frequency omega. And when we went to the rotating frame, we subtracted little omega from big omega. And the way that we interpreted this was that a spin was seeing a static field that was pointing in some direction, and it would precess around that static field. And that static field we would call B effective. It's h bar big omega minus little omega over gamma times the unit vector in the z direction plus b1 times the unit vector in the x direction. Note that z hat and x hat here are unit vectors, not operators. So now we're going to make an abstraction of this. We're going to forget about the cyclotron resonance problem. I'm going to simply ask the question, what happens if we look at the limit omega approaches 0 and omega approaches infinity? So if omega approaches 0 and big omega is very large and b1 is very small, we essentially have a magnetic field that is pointing along the z-axis. And if we look at the ground state of that system, that will have a spin up that lies along the z direction. Now if we imagine increasing omega until it becomes plus little omega, until it becomes plus infinity, what we now have is the magnetic field is pointing in the minus z direction, or essentially in the minus z direction. And now the ground state will be a spin oriented in the minus z direction, or a spin down. And what we can imagine if we did this slow enough is that the spin will continue to precess about the instantaneous magnetic field, but eventually at the end it'll be pointing downward if it started upwards, because it will end up precessing around the magnetic field that's the final magnetic field, which is pointing downwards. And the upshot of this is that we can think of this as a procedure by which we can flip the spin not in the way we did it with cyclotron resonance by applying a rotating field and just waiting long enough for that rotating field to act and cause the spin to flip via resonance. Here what we're doing is we're essentially going to move the magnetic field from pointing along the positive z direction to pointing along the negative z direction. We can think of doing that essentially by rotating the field if you like. And if we do that slow enough, the spin will continue to precess about the instantaneous field and will eventually be pointing downwards. So that's essentially the physical problem you should keep in mind for what is called the Landau-Zener problem. And we can study it using just 2x2 matrices. And one way that you can represent this Hamiltonian is in the way that I've illustrated here for you. The Hamiltonian is a 2x2 matrix. It has some off-diagonal matrix elements that are V. That's the little b1 field that we have. And then we have the rest of the Hamiltonian is proportional to Sz, and the proportionality is a number delta times t. It's not an infinitesimal step in time. It's just a linear variance in time with a delta times t. And so that will go from minus infinity to plus infinity as we vary time over the full domain of time, from early times to late times. And if you want to write that in terms of Pauli matrices, it's delta times t times sigma z plus v times sigma x. Now, this is a simple 2x2 problem. We can very quickly find its instantaneous energy eigenstates. To do that, we first subtract E times the identity matrix and take the determinant. We'll get delta T minus E multiplied by minus delta T minus E minus V squared. You can immediately multiply out that first set of products. You'll get E squared minus the quantity delta T squared minus V squared. You move the delta T squared and the V squared to the other side. We get E squared is equal to delta T squared plus V squared. Take the square root of that and we get the eigenvalues. So the energy eigenvalues, there's two of them. We'll call them E plus minus. They're just plus or minus the square root of the quantity delta T squared plus V squared. Now we can plot those as a function of time. Notice that when t equals 0, those eigenvalues are plus or minus V. When t gets very large and approaches plus or minus infinity, those eigenvalues are plus or minus delta times t, absolute value. And so it looks like the plot that we have here, where we have these two parabolas and they don't cross. They look like they should cross, but then they have what's called an avoided crossing. And they're always separated by a distance where the minimal distance is equal to 2v. The dashed line shows you what you would get if you took the limit where v equals 0, where you really would have a crossing of two lines and would act like two linear lines that are crossing each other. So we can go ahead and find the eigenvectors of this. And because the two eigenvectors are orthonormal vectors, we can always write them in the following form. Cosine theta over 2, sine theta over 2 for the plus, and sine theta over 2, there should be a minus sign in there, minus cosine theta over 2 for the minus state. So there's a typo there. The lower term should have a minus sign on it. And theta would be some function of time. These are what we would call the instantaneous eigenvectors. And this form that I've written above holds simply because I need to find two orthonormal vectors that are parametrized by a single parameter. Now, in order to solve the problem, we want to force it into finding what theta of t is. So we're going to take this and we're going to solve for the plus state, and we're going to say h of t acting on the plus state is equal to e plus acting on the plus state. Well, h of t from the matrix acting on this plus state, we're going to get a delta t times a cosine theta over 2, and we're going to get plus v times sine theta over 2, and that's going to equal the energy eigenvalue, which is square root of delta t squared plus v squared with the plus sign, multiplied by cosine theta over 2. So that's looking at the top component of the plus vector. Now, because this is an eigenvector-eigenvalue equation, once we've solved that equation, because we put in the correct eigenvalue, that will actually solve the whole problem. So now what we do is we just do a little bit of rearranging. We bring the cosine terms to the left-hand side, the sine terms to the right-hand side, and then we divide to get an expression for tangent theta over 2. And tangent theta over 2 will equal the square root of delta t quantity squared plus v squared minus delta t divided by v. So that's an expression for tangent theta over 2. Now it turns out after you look at these equations for a while, you recognize that it's more convenient to write this in terms of tangent of theta, and that's what we're going to do now. So we're going to first work with a half angle formula. We're going to write tangent of theta as tangent of theta over 2 plus theta over 2. And using the angle sum formula for tangents, we'll get tangent theta over 2 plus tangent theta over 2 divided by 1 minus tangent squared theta over 2. Now we plug in the values for tangent theta over 2. In the numerator, we get the square root minus delta t divided by v. And then in the denominator, I get 1 minus the quantity square root minus delta t quantity squared divided by v squared. Now we go ahead and we multiply out that denominator. We bring the v squared up into the numerator, and we're going to get a v squared minus a delta t squared minus a v squared. The cross term will give us plus 2 delta t times the square root, and then we're going to get a minus quantity delta t squared. And you see the v squareds are going to cancel. I'm going to be left with a delta t with a minus 2 delta t squared. You see I can factor a 2 delta t out of that, and I'll get the square root minus delta t. And you see that's exactly the same factor as I have in the numerator. So those two terms are going to cancel, and I'm left with this nice simple form, v over delta t. So tangent of theta ends up being a very simple formula, even though tangent theta over 2 is a pretty complicated formula. Okay, so we've now learned that the angle satisfies tangent theta equals v over delta t. Let's look at what this is going to be in our two limits. As t goes to minus infinity, if I assume v and delta are both positive numbers, as t goes to minus infinity, I'm going to find that the tangent of theta is going to 0 from the negative side, and so that's going to be approaching pi. And as theta goes as the time goes all the way to 0, the tangent is going to diverge, and then it's going to go to infinity, and it's going to go to 0 from the positive side. So I'm going to run from pi through pi over 2 back down to 0. And so theta actually is a decreasing function of time. And we're going to explicitly calculate the derivative of theta with respect to time below. All right, so now we have to recall the first lecture that we did on time-dependent problems. And there what we did was we expanded our wave function in terms of instantaneous eigenfunctions. We called them n of t, and so we had a sum over n cn of t times n of t. Of course, in this problem, there only are two eigenstates, so that sum only has two terms. And we use the fact that h acting on n is equal to en of t times n of t because these are instantaneous eigenstates. Then when we plug into the time-dependent Schrodinger equation, I over h bar d by dt is psi of t, we pick up two terms, one where the derivative hits the cn of t, and one where the derivative hits the state. And of course that's equal to h acting on the state, and because these are instantaneous eigenstates, we can immediately replace the h acting on n by en of t acting on n of t, and so we get this expression sum over n cn of t en of t times n of t. Now we're going to work with a very special form for cn of t. We're going to write cn of t is equal to alpha n of t, some complex number multiplied by an exponential of minus I over h bar, the antiderivative of en of t prime. Now if I take the derivative of that, I h bar d by dt of cn of t, I'm going to pick up two terms. I'm going to get I h bar d by dt of alpha n of t, and then I'm going to get, in addition, I'm going to pull down a factor of en of t from that exponent, because I have to take the derivative of the exponent, and that says evaluate the integrand replacing t prime by t, so I get minus I over h bar en of t, but I'm multiplying by I h bar, so that cancels the factors in front and just leaves me with an en of t. So now when we plug that into our equation, you see it's very nice. It's going to cancel the en of t from both sides, and we're going to get the following result. IH bar sum over n d by dt of alpha n of t multiplied by this exponential factor times the instantaneous eigenstate plus alpha n of t times the exponential factor times the derivative with respect to time of that state. That whole thing is equal to 0 because the en of t terms cancel on both sides. Now we multiply both sides by m of t, and we're going to be able to isolate the following equation. D by dt alpha m of t is equal to minus the sum over n alpha n of t, this exponential where we now have a difference of instantaneous eigenvalues, en of t prime minus em of t prime, because we divided by the exponential factor on both sides, is equal to the overlap of m of t with the derivative with respect to time of n of t. So that is now our equation of motion for this time-dependent wave function when it's written in the form sum over n cn of t n of t, and cn of t is written in this form alpha n of t exponential minus I over h bar antiderivative of the instantaneous eigenvalue with respect to time. Okay? Now, for us, we can imagine that we start in the lowest energy state, which is the minus state. And if delta approaches 0, the ramping in time is very slow. Then what we expect is the state essentially remains in minus with the probability of plus being very small. So alpha minus of time is approximately equal to 1, and alpha plus of minus infinity is equal to 0. This approach where we think that everything is varying very slowly, it actually has a name to it. It's called adiabatic perturbation theory. And if you think carefully, the derivation we did above actually holds for any problem that you might imagine looking at, not just this particular Landau-Zener problem. It's only the stuff that we're going to be doing in just a moment that relates it to the Landau-Zener problem, because we only have two instantaneous eigenstates. Okay, so now what we find is alpha plus of t. After integrating it, we have this differential equation. Let me remind you what that differential equation is. If I integrate that differential equation, what you find is we're going to get alpha plus of infinity is equal to the integral minus the integral from minus infinity to plus infinity dt of alpha minus of t e to the minus I over h bar integral with respect to t e minus of t prime minus e plus of t prime dt prime times the overlap of plus with the time derivative with respect to minus. Now you might think there should be a second term in there, which would be an alpha plus of t multiplied by no exponential term, because we would have an e plus minus an e plus, and then the overlap of minus with the time derivative with respect to minus. But we're going to show you that that overlap is actually equal to 0. So let's go through that right now and verify that this equation is actually the differential equation that we get. So to verify that minus d by dt of minus is equal to 0, what we're going to do is we're going to take the time derivative of plus when it's written in this form that it has the thetas in it. We're going to now talk about the plus state and the minus state. So remember, the minus state is supposed to have this minus sign and the cosine theta over 2 in it. And the plus state is as it is written. So cosine theta over 2, sine theta over 2. And the minus state should be sine theta over 2 minus cosine theta over 2. Okay. So now we come back down. We're going to calculate this derivative of the plus state. The plus state is cosine theta over 2, sine theta over 2. I'm going to pull a minus sign out when I take the derivative, so I'll get minus d theta dt 1/2. Derivative of cosine is minus sine, but I pulled the minus sign out, so I get sine theta over 2. Derivative of sine is cosine, but I pulled a minus sign out, so I get minus cosine theta over 2. And that's just equal to minus 1/2 d theta dt of the minus state. When I calculate the time derivative of the minus state, I'm going to have a derivative of sine theta over 2. That becomes cosine. I'm going to have a derivative of cosine theta over 2. That becomes minus sine theta over 2. But there's a minus sign in the minus state, so that becomes a plus. There's actually a typo there. That should be plus sine theta over 2. So I get d theta dt times 1/2 times cosine theta over 2 plus sine theta over 2. I have blurred out the minus sign that's in the notes so that you don't get confused by it. And of course, that's equal to the plus state. So I get 1/2 d theta dt times the plus state. Now let's take the overlaps of these derivatives with respect to the plus and minus states. Plus d by dt plus and minus d by dt minus, they're both equal to 0 because the derivative was always proportional to the other state. Of course, we kind of know that because the plus states and the minus states are always normalized, and the derivative of a normalized state must always be perpendicular to the state. Now we find plus d by dt of minus is 1/2 d theta dt, and minus d by dt plus is minus 1/2 d theta by dt. So now we plug into our integrated form for alpha plus of infinity. We get minus 1/2 integral minus infinity dt d theta dt e to the plus twice I over h bar integral with respect to t of the square root of quantity delta t prime squared plus v squared dt prime. The 2 occurs because e plus is the negative of e minus. Now remember, we derived above that tan theta of t is equal to v over delta. We're going to now use the chain rule, take the derivative of that. We'll get secant squared theta d theta dt is equal to minus v over delta times t squared. And then we solve for d theta dt. We get minus v over delta t squared divided by secant squared. That means we divide by 1 plus v over delta t quantity squared, because 1 plus tangent squared is equal to secant squared. Now when we simplify this all out, we get it's equal to minus v times delta divided by quantity delta t squared plus v squared. So we have an explicit form for the derivative with respect to theta, and that enters into this overlap between plus d by dt and minus. We have an explicit expression for the exponential, and we can approximate alpha minus of t by approximately 1 if we would like. And when we do that, we get alpha plus of infinity is approximately equal to 1/2 the integral from minus infinity to plus infinity dt v delta over delta t squared plus v squared e to the 2i over h bar any derivative with respect to t of the square root of delta t prime squared plus v squared dt prime. Now, you can evaluate this using complex analysis, or you can try and plug it into Wolfram Alpha or Mathematica, see if it'll do the integral for you. And what you get for this approximate relation is that alpha plus of infinity, if you integrate this thing, you actually get pi over 3 e to the minus pi v squared over 2 delta. Now that's an approximate answer, but if I squared that to get the probability to stay in the plus state, that would equal pi squared over 9 e to the minus pi v squared over delta. And remember, that is just an approximate formula. The correct answer is the one that was worked out by Zener in the early 1930s using those parabolic cylinder functions which solve this Weber's equation. And what he found was the probability to stay in the plus state is e to the minus pi v squared over delta. So that coefficient that was approximate, that's pi squared over 9, should actually just be equal to 1. And this answer that Zener got actually holds for all delta, not just in the limit as delta goes to 0. Okay, so as delta is made large, the probability to not flip the spin actually grows. And this is a non-perturbative result in delta because it's going like an exponential of some number divided by delta. If you try to do a power series expansion of that or a Taylor series expansion of that, you find all of your Taylor series coefficients are 0, and there is no Taylor series expansion for it. So that's what those kinds of expressions are called non-perturbative results, because I cannot express them via a Taylor series expansion. And that tells us that if we tried to solve this problem by time-dependent perturbation theory, it would not work well. And this is because the time-dependent piece of h of t is very large. It goes from very large to very small, back to very large again. And it just the dominant piece of the Hamiltonian is actually the time-dependent piece. And so thinking of breaking it up into a time-dependent piece and a time-independent piece is not a wise idea. Now, to think about this in pictures, if we look at those instantaneous energies, we start all the way at left in the lowest energy state. And if we don't change, we continue on that path. If we do change, we jump, and the jumping typically occurs around the point of closest approach. We jump to the other branch and we move up. And that's the probability not to flip. It's e to the minus pi v squared over delta. And the probability to flip is 1 minus e to the minus pi v squared over delta. And now in the adiabatic limit, that's when delta goes to 0. So when we do this very, very slowly, we always flip the spin. And in the diabatic limit, where delta is very, very fast, we never flip. We always stay in the same state. And you can think of it as traversing so rapidly that we just tunnel across the gap and stay and make the switch from the ground state to the excited state instantaneous energy curves as we make the transition and change the Hamiltonian very quickly from one state to the other state. And of course, the true case is somewhere in between these two. And what is nice is that this actually is an exact formula that gives you the answer. Let me give you just one more discussion. There are two different ways that you can imagine trying to solve this problem using the kind of analysis that we've done in the class. One way is you can break up the time into a bunch of little pieces with a time state big delta times t, and can calculate what the exponential is of the time evolution operator at each time using the exact formula we worked out for Pauli spin matrices for the exponential of a matrix. And you can plug that into a computer, and you could just take the product of all of those guys. And if it doesn't look accurate enough, you can make your time step big delta t smaller and run it again. Of course, you're not going to run exactly from minus infinity to plus infinity. You'll have to pick some large negative time to start and some large positive time to end. But you can very easily write a program, probably take you about an hour to run this through, run the calculations, and then you can get all the different results, and you can compare your results to the exact answer and see how it works. Now, there's another way that I think might also work. I haven't actually tried to do this myself, but if you looked at taking the exponential of two consecutive Trotter factors, you can multiply those two factors out. And it's a complicated expression that you'll get after you multiply that out. But of course, we can write any 2 by 2 matrix as the exponential of something times the identity plus a v dot sigma. And so you could actually go and figure out what is that something times the identity and the v dot sigma when you multiply those two out. And you could use that to figure out what do you get when you numerically calculate this entire chain. And you might actually be able to get an analytic formula for what that expression is. It might be that that expression is something that you would end up writing as an integral, but that integral would be the integral that would go into the evaluation of the time-ordered product and would tell you ultimately about the probability to stay in the same state or not stay in the same state. I'm not sure whether or not that technique would exactly work, but it certainly seems feasible that you could try to work out the details of how that works. It might ultimately give you some kind of a differential equation that you would have to solve, and maybe it turns out being the same as this Weber equation or something else, but there is another strategy that you also could try. Okay, that's all for this lecture, and we will return with more time-dependent problems in Lecture 31.